Hi everybody, Mrs. Danielson here, and today we need to talk about the ambiguous case of the law of cosines. Just a particular thing that we need to watch out for when we're working with the law of sines. We love the law of sines, it's very easy to use, but every once in a while we have this particular thing we just kind of need to watch out for with the law of sines. Okay, the law of sines has the ambiguous case occurring when we have a side, and an angle. In particular, it's just when you have this particular thing, side, and an angle, and you're using the law of sines. Let's write down our law of sines just to remind ourselves what it is. It's sine A over A equals sine B over B equals sine C over C. Okay, so let's take a look at this triangle right here. And what we want is we want for there just to be one triangle that comes out of this situation. Okay, it could be that there could be more than one triangle resulting, but we only want one. Let's see what happens when we try to solve this one. Okay, I have two sides and one angle. I do know angle A and I do know side A. So I'm going to use angle A side A. So that would be sine 45 degrees over 7 square root 2. I know side B. I don't know angle B. So I'm going to solve for angle B, sine B over 7. And I'm going to solve that for sine B. So I'm going to cross multiply and get 7 sine 45 degrees is 7 square root of 2 sine B. Okay, divide by 7 square root of 2. Okay, and you get sine B is 7 sine 45 degrees over 7 square root of 2. Okay, so that all simplifies actually. It simplifies to 0.5 or 1/2. Okay, what angle has a sine of 1/2 or 0.5? Well, 30 degrees has a sine of 1/2. But there's another angle that actually has a sine of 1/2. Okay, if we think about our quadrants here, 30 degrees has a sine of 1/2, right? Sine is opposite over hypotenuse, right? 1/2. But over here in quadrant 2, opposite is 1, hypotenuse is 2, the reference angle is 30, and the angle is 150. So that means that an angle of 150 also has a sine of 30 degrees, right? Because 150 degrees has a reference angle of 30. So that means B could be also 150 degrees. Two different angles that have a sine of 1/2. Well, if we think about angle B, I could put a 30 in here. Let's just say that could be a 30. And that would be okay, that would make sense because that would leave me with 180 degrees minus 75 degrees for angle C. What if I tried putting in 150 though? If I tried putting 150 degrees in there for angle B, would that work? It wouldn't, because that means A and B equal 195 degrees, and I'm already out, right? I can only have 180 degrees for a triangle. So that means that 150 degrees does not work for this triangle. So B has to be 30 degrees. Okay, now that you know that, I can proceed with solving for the rest of my triangle. I can calculate angle C. And once I have angle C, I can solve for sine C. What happens though if I can't eliminate one of the two choices, right? What happens if they both work? right? Well, that's the situation when we have an ambiguous case, where there's not just one triangle. It turns out that there's two. Okay, so let's take an example of an ambiguous case. Here's a triangle. We're given A, B, and C. And let's say we're given angle A is 45.3 degrees. And side B is 185.2. And side A is 167.1. Okay, so it's two sides and an angle. Okay, we need to solve for our two angles and the one missing side. Okay, so we want to use sine A over A, and we want to use sine B over B. Again, we want to use A because we know the angle A and the side A, and we want to use B because we know side B, right? So we're going to use this and solve for angle B. Okay, so we substitute in what we know, 45.3 degrees over side A. We're solving for angle B, and here is our side B. So far the same as any other problem, right? We cross multiply, and we get 167.1 sine B is 185.2 sine 45.3. And then you just divide by 167.1. Okay, so the sine of angle B is equal to 185.2 times the sine of 45.3 degrees divided by 167.1. So you put that in your calculator and you're going to get something that is about 0.7878. Okay. Now when you use the inverse function on your calculator, that's going to give you that angle B is about 52 degrees. Okay. Now there's another angle that has that same sign, like we said before, right? This angle in the first quadrant, that has a sine of 0.7878, but the angle over in quadrant 3 that has a reference angle of 52 also has that same sign. Okay, so this angle that's 180 minus 52 has the same sign, right? This one right here, 180 minus 52, that's going to have the same sign of 0.7878. Okay, so that would be 180 minus 52 is 128 degrees. Two possibilities, two angles with that same sign. Okay, could they both work? Maybe. If I plug a 52 in there for B, would that work? That would, and it leaves me plenty of room for angle C. If I plug in a 128 for B, does that work? Yeah, that's less than 180. And it does leave me a smidgy little room for angle C, not a ton, but it does mathematically give me a little space. So what that means for this situation, I have two possible triangles. There's not just one, but two. And so that means I have to proceed solving two separate triangles. So I have one triangle that I'm moving on with that's an acute triangle, B and C, with 45.3 degrees, 185.2, 167.1, and 52 degrees. And then I have a different triangle where B is going to be this big obtuse angle of 128 degrees. 45.3, this might not be drawn totally to scale, but you get the idea. Okay, and now you have to proceed with solving, completing to solve both of these triangles, right? So on this one, angle C is going to be 180 degrees minus 45.3 minus 52 degrees, right? So angle C for that first triangle is going to be 82.7 degrees. And angle C for the obtuse triangle is 45.3 minus 128. Oh, subtracted from 180, right? Got to squish that in there. Minus 45.3 minus 128. What does that leave for angle C? That teeny tiny little slivery angle up there, right? It only leaves 6.7 degrees. Okay, so we have an 82.7, and we have a teeny weeny little 6.7 degree. And then to finish off the problem, you've got to find side C, right? So you pick one of the other two angle pairs, maybe A. You could use B, right? So sine A, I'll use sine A over side A. And then we're looking for C, so sine of angle C over side C. And then over here, you can do the same thing. Sine of A over side A. And you're going to use your sine of C over C. Cross multiply to solve for your side C. Feel free to always pause the video, take some time, right? Do the calculation on your own and then see if you get the same thing I have, right? So side C is going to be that little calculation you do there on your calculator. Okay, so side C on the first triangle is going to be 233.2. Go ahead and take a look at that. Does it make sense? Now I've got everything in that first triangle. Is the longest side opposite the longest angle? Is the shortest side opposite the smallest angle? Everything looks good there with that triangle. And then just finish with your other triangle, cross multiplying. And then dividing by the sine of 45.3. Again, this is the same steps we usually do when we're solving with the law of sines. Plug that into your calculator, and what do we get for that side that's opposite angle C? Right, it should be something fairly small, 27.4. Come back up, plug that in. Should be the smallest side because it's opposite a teeny tiny angle. And it is definitely smaller than the other two sides. So it looks like everything's proportional the way it should be. Okay, and there you go. Okay, so that is the ambiguous case of the law of sines. You just need to watch for it when you have two sides and one angle, that there's the possibility that there's just one triangle, but there's also the possibility that there could be two. Everybody have a super day, and thanks for learning about the ambiguous case of the law of sines.